Hi everybody, welcome to another video in course Algebra, section 4.2, logarithmic functions. So what is a logarithmic function? So the motivation is, say when we have 2 to the x power equal to 8, and we say what is x? Well, by inspection, 2 to the third power is equal to 8. So x is equal to 3, just by inspection. And then we say, what happens if we have 2 to the x power equal to 10? Then 2 to what power is equal to 10? Well, in that case, we don't know the answer yet. But at least we know the question. 2 to the what power? So what is the power when 2 raised to that power is equal to 10? And that's exactly what we define a logarithmic function. So if we let x be only positive and b is positive, not equal to 1. So this is the condition for the base of exponential function. We write y equal to log base b of x, which is equivalent to b to the y equal to x. So b to what power is equal to y? So that the answer to that question is going to be y. So once again, b to what power is equal to x? B to what power is equal to x, and that what, answer to that what is going to be y. So by the way, when we write log, it's going to be log the base is the subscript, and the x is on the same level as the log. So the log and x on the same level. The b is a subscript, which is also called the base. And we can interchange between the logarithmic form and exponential form in this case. Alright, so once again, b to what powers is equal to x, and the answer to that question is y. Now, so which is b to what powers is equal to x, and of course that case is y. So we can interchange between these two. So what we do here is we see the equal sign will stay, the log base b will stay, and then we switch x and y. So x and y switch places. The base b is still the base b, the equal sign still there. So remarks. Exponential function is a one-to-one function. So the inverse exists, and the inverse is an exponential function of the same base. So those two are inverse of each other, and all the properties of inverse will carry. And we'll see that when we look at the graphs and characteristic of exponential function. But for now, definition is all we have. Once again, if we want to switch between exponential form to logarithmic forms, what we do is the equal sign will stay, and then we just swap. So the equal sign here, just write out the equal sign first. The base, in this case the subscript is 7, so the base is going to be 7. And all I do is just switching the 3 and x. So 3 and then x. Write the equal sign, and then the base, the subscript, and then switching the two numbers. 16 go to this side, and the 4 go to this side as the exponent. When we swap, it will become the exponent. Right, same thing. The equal sign will stay, the base will stay, and swap the negative 2 and 1 over 25 to the other side. Equal sign will stay, the base is 4 will stay on the same side, and then we just swap the other number. The 3/2 go to the other side, becomes the power, the exponent, and the 8. So that is where we change from logarithmic function to exponential function. It's easy enough. Equal sign stay, the base will stay, and then swap. Same thing, I should say in the reverse order. when we change this back to logarithmic function, so the equal sign will stay. The base is 12 will stay. However, in the log, we have to have the logarithmic function. And then the base, this case 12, so that will be a subscript. And then we interchange x and 2. Same thing here. We introduce the log, the base is b, and then we interchange 3 and x. So x goes here, the 3 goes there. Right? Equal sign will stay. The log, base 3, so that's a subscript, and the other two number will swap places. And then same thing here, equal to, the base is 8, and swap 16 and 4/3. So when we see this is 8 to what powers is equal to 16, and the answer is 4/3. When 8 to raised to 4/3 power is 16. Right. Now, let's evaluate this logarithmic expression. Right. So 2 to what power is equal to 16, right? We actually don't know that yet, so we're going to write that is equal to x. And then we can swap to bring to exponential form. The equal sign will stay, the base is 2, and then x and 16 swap places. So 2 to what power is equal to 16. And since we have 2 to the 4th power is equal to 16, x equal to 4. Right. If we don't know what it is, make that equal to x, and then we'll swap to exponential form. The base is 25, equal sign, x and 5 swap places. Right. Now this is a little bit more complicated. 25, we can write 5 square, right? And 5 here just to the first power. Now, power to another power, so we just multiply the exponent together. 5 to the 2x equal to 5 to the first. Now, both of them have the base of 5. The exponent should be equal, so I have 2x equal to 1. So x is equal to 1/2. So 25 to the 1/2 power is equal to 5. Alright, next. Log base 7 of 1 over 49. Again, if we don't know, make that equal to x. And now we swap. The base of 7. X go to the other side, 1 over 49 go to this side. Now, 1 over 49, if we move from the bottom to the top, that becomes 49 to the -1, right? 49 to the bottom to the top. So we have 7 to the x equal to 49 is 7 square, and exponent to another exponent, we multiply those. 2 times -1 is -2. So base of 7 to the x power, base 7 to -2 power. So x equal to -2. Right. Now once again, we don't know what this is equal to, so make that equal to x, and then we swap to exponential form. X goes here, and 5 square root of 2 goes to the other side. Now, the fifth root of 2. The fifth root of 2, we can write to the fifth root of 2 to the first power. So we can have the power on the top, the root at the bottom. I don't know why I write 5 here where the base is supposed to be 2. So in that case, we say x is equal to 1/5. So 2 to the x power is equal to the fifth root of 2 to the first. And we write that. So x is equal to 1/5. Right, log base b of b. Don't know that, make that equal to x, and then swap. B is the base equal to. Now b is the base. This b and x will interchange. B go to that sign, x go to that sign. And this by default is to the first. Anything to the first power with itself. So here we have x equal to 1. Right. Once again, if we don't know what it is, make it equal to x, and then we swap. So b to the x power is equal to 1. Now, everything to 0 power is equal to 1. So in this case, x is equal to 0. Right. So once again, this read as, let's look at this one. 7 to what power is equal to 1/49? And the answer is -2. So we say 7 to the -2 power is equal to 1/49. Now let's look at the graph and characteristic of logarithmic function. So before we do anything, just a review. We have exponential function. In this case, b is greater than 1. We go to this point and have the horizontal asymptote. So that is exponential function. Now, remember, we did mention in the previous section, previous section. What I mean is, the beginning of this section, exponential function and logarithmic function, they are inverse of each other. So when we do the inverse, we interchange the role of x and y. So notice that in exponential function, we have the point x equal to 0, y equal to 1. So when it becomes the inverse, it will become the 1 and 0. And the graph of logarithmic function goes like this. So it is f of x equal to log base b of x. In this case, the b is greater than 1. So normally we swap all the points x to y, y to x. The horizontal asymptote will becomes the vertical asymptote. So we switch x and y intercept becomes x intercept, and horizontal asymptote becomes vertical asymptote. We have one nice characteristic of inverse function. The graph will be symmetric on the line y equal to x, and in this we do have it. So this is the graph of logarithmic function. Right, now we'll do the same thing, but this time the base is less than 1. So the exponential function goes like this. But this time the base is between 0 and 1. But regardless, still go to the point 0 and 1 and have the horizontal asymptote as the x-axis. Now, when we swap, that point becomes the x-intercept of 1, 0, and the horizontal asymptote of the x-axis becomes the vertical asymptote of the y-axis. So this is the graph. A block base b of x where the base b is less than 1 but still greater than 0. So the horizontal asymptote becomes the vertical asymptote and the point x-intercept, y-intercept become x-intercept, and once again the characteristic of inverse function, the graph with symmetric on the line y equal to x. So the graph of logarithmic function, we have two important characteristics, is the vertical asymptote and the point 1, 0. So we have the characteristic, it have the x-intercept of x equal to 1, y equal to 0, and have the vertical asymptote of the y-axis, or x equal to 0. As for domain and range, we only have the x positive value for x, but the range can be any real numbers. So if we look at the properties and characteristic of logarithmic function, if we compare, this is exponential function. You see domain and range switch because we just switch in x and y. No y-intercept, no x-intercept. X-intercept is 1, 0. Y-intercept is 0 and 1. So pretty much we switch on the x to y, horizontal to vertical. And we have the graph and characteristic of logarithmic function, which go like this, increasing when it's greater than 1 and decreasing when it's between 0 and 1. Now let's sketch the graph. So for this one, log base 2 of x minus 1 plus 1, the basic graph. Is y equal to log base 2 of x. So characteristic go to the point 1, 0 and have the vertical asymptote. So, and this is increasing. So like that, it just keep going. Right? So that is log base 2 of x. Now we have is the minus 1 and the plus 1. Minus 1 here. We move 1 unit to the right. And plus 1. One unit up. So 1 unit to the right. This point 1 unit to the right, and the vertical asymptote will be 1 unit to the right. So graph, and then 1 unit up. When go 1 unit up, the vertical asymptote is still the same line, but the point go up. So that it's just a sketch. Right. So when the base is bigger than 1, it is increasing. When base less than 1, it is decreasing. So like what we have here, the basic graph. Is y equal to log base 1/2 of x. So it is less than 1, the base is less than 1, so it is decreasing, but still go to the point 1, 0, and vertical asymptote still the x-axis, and it's decreasing, right? Y equal to log 1/2 is the base of x. And now we just have the plus 1. So we just want 1 unit to the left. This point 1 unit to the left, and the vertical asymptote, the y-axis, become this. And so we have it's like that. Just a sketch. Just move 1 unit to the left. Right. So we have the graphs and characteristic of logarithmic function. Now we go to some properties of logarithms. Now before we do that, let's recall the base e, or the number e is that number. Now we define two logs. The natural logarithm is when the base is e. In that case, we just write ln. So ln means the log base e. The common log is so common that we don't need to write the base. So for the common logarithm, the base is equal to 10. So when we write log x, we mean the base is 10. And when we write ln of x, we mean the base is e. Alright, so we have the general log of base b. The common log, the base is equal to e. The common log, the base is equal to 10. And the natural log, the base is equal to e. Right. Now we have these properties. Well, how do we know these properties? Well, it's easy if we just swap that to exponential form. Right? I forgot there's a typo here. Very bad typo. B log base b of 1 equal to 0. Sorry. Right. Now we can swap. The equal sign will stay. The base will stay, but this time it's the same level. 0 and 1 will be swapped. So anything raised to 0 is 1, which is check. And next, the base is b will stay, and 1 b swap. Anything to the first power is itself, which is also good. Now, equal sign. Now the base is b, right? We swap the whole b to the x and x. So x go to this side, b to the x go to that side. They're the same. So it's good. And then next, this is b to log base b of x. The base here is b. If I write to logarithmic form, I swap x and log base b of x. The x goes here and log base b of x go to the other side. And that also check. So the last two properties come from these two properties come from the inverse function. What I mean by that is the definition of inverse function. So that's what we have. So that is just the log, some common properties of the log. Right. Now, all we do is just replace the 10 into b, and we have the properties. So log, the base here is 10. Just replace 10 to b. Replace 10 to b. Replace 10 to b. Right. Once we replace, notice that the common log, we do not need to write the base 10. So it actually should be this is a common log, so we do not need to write the base 10. Right. Again, no need to write the base 10. And then no need to write base 10. and no need to write the base 10. So to the x power equal to x. I should write smaller to begin with. Right. So that properties in common logarithm. Now the base is e. Just replace e into b. So log base e of 1 is equal to 0. And log base e is the ln. So I just write ln of 1 is equal to 0. Log, now replace e into b, and the log base e is just ln. So ln for log base e of e is equal to 1. Now replace e into b. So we have log, log base e, which is ln, and then of e to the x equal to x. And then replace e into b, and then log base e is ln. Right. So those are the common or very general logarithm. General properties of logarithmic functions. Right. So it's easy enough. Right. Look at these properties. This is just from the inverse function. So what we see here, of course, we can always based on definition, but it would be better if we just do that without definition. So what we see here is, if we have the log base b and b, so pretty much that cancel out. Log base b and e will cancel out. That's equal to x. And that goes the same thing for common log and the natural log. Ln and e cancel out. Ln and 10 cancel out. 10 to the log cancel out. E to the ln cancel out. Right. So we use that instead of based on the definition. It will be easier to do. Right. So let's evaluate this. By the way, bottom line is, if we don't know what it is, if we don't remember any of these properties, we can always write that equal to x, and then swap this to exponential form, 4 to the x power 4 to the 5th. So we swap to exponential function, and then we say x equal to 5. But the log base, the base is 4 of the log, and the 4 here cancel out. That's just equal to 5. So where we have the log of the same base, exponential of the same base, those two cancel out, and what's left is left. Ln and e cancel out, we know that, so this is just going to be equal to 2. So if we don't want to write like that, we can always write as log base e for ln. Once again, the base of the log is e, the base of the exponential also e, they cancel out, and we have 2. Of course, we can always write as a definition and then swap to exponential form. That also works. Right. Log 10 to log of 5. This is the common log. So we don't need to write the default base 10. But once again, exponential of base 10, the log of base 10, those cancel out, and we have 5. right? Now this, we see that log of any base of 1 is equal to 0, so this is equal to 0. Of course, if we're not sure about that, we can always swap to exponential form. 7 is the base, equal, swap 0 and 1, and so that check out. Anything raised to 0 power is 1. Alright, so that's what we have. Now we have log base 3 of 27. Again, if we don't know what it is, we can always make that equal to x, and then we swap. So 3, and then the x go to this side, 27 go to the other side. And then we can write 27 is 3 cubed. Now both of them have base 3, so x is equal to 3. We can always do that. If we don't know what the log is, make that equal to something, and then swap to exponential form, right? But here I will do it differently. 27, I will write 3 to the third power. Now, we have the log base of 3, the exponential base of 3. That cancel out, we have 3. Right, next we have log of, this is a common log, so let's just rewrite this as log base 10 and 0.001. That is like 1 divided by 1000. Which we move to the top, it becomes 1000 to the negative 1. Now 1000 is 10 cubed. And multiply the exponent together. We have log base 10 and the exponential base of 10 cancel out. We have negative 3. Right. Now last one is a little more complicated. Log base 1/2 equal to 8. So 1/2 to what power is equal to 8? Well, just look at this first. Log of 1/2 of 8. Don't know what it is, equal to x. Now we swap. 1/2 to the x power is equal to 8. Now 1/2 is 2 to negative 1. And 8 is 2 cubed. Exponent and exponent. Multiply the exponent. Negative 1 times x, negative x. And finally, both of them have base 3, base 2. So negative 2 is negative x is equal to 3. So x is equal to negative 3. Right. So certainly we can do it that way, but here we write a little differently. So the 8 here I can write as 2 cubed. Right. Now the 2 cubed, if I move to the bottom, it becomes 2 to negative 3. And then 1 we can also write to negative 3 because 1 to negative 3 is still 1. So we can bring both of them inside. The power of negative 3. And now we have log of base 1/2. And the base of 1/2 on the exponent cancel out. So that is negative 3. Right. Of course we do like this perfectly fine. Now ln of e to negative 10. ln by default is log base e. So we have log base e and exponential base e. that case I would just have negative 10. Once again, if we don't know what it is, we can always write that in this form, and then we swap and then solve for it. Right, here we have the domains of this function. So the domain of this function, remember for logarithmic function, what is the domain of? You see the graph of the logarithmic function. This is only on the right side of the y-axis, so it only take the positive values. So the domain, the argument of the log must be positive. So in this case, I'm just going to say it doesn't matter what the base is, what we put in the argument of the log must be positive. So in this case, we just have x minus 2 have to be positive, greater than 0. So plus 2 on both sides. So we have x greater than 2. So that is the domain. So if we draw the line on the right side of 2, so domain is going from 2 to infinity. Right. Similarly, this is base 10. We have the argument of the log, which is x squared, and we require it to be positive. Well, we're going to use the graph to solve this problem. X squared is that. Parabola go to the point 0, 0. So we want it to be positive, meaning that we do not want to have this point. The graph, everything there was good, so meaning it could be everything but 0. Could be on the right side or the left side, but it cannot be 0. So in this case, domain is negative infinity to 0 or 0 to infinity, but cannot be 0, because when we have x equal to 0, y equal to 0, for any other values of x, x squared is positive. So in this case, that's what we have for domain of this function. And with that, I stop section 4.2 here, and thank you for watching. See you in another video in course algebra.